In this video, we will look at two applications of how an integral can be used. So one application is this average problem. Now, to do an average, what we do is add up all the values and divide by however many there are, right? But something like temperature that's always fluctuating, how do you add a set of infinitely many points there? Because it is constantly changing. That's where we do integral. Okay, an integral, remember, is finding the area under a curve. So if I have all these different temperatures, and this is not an accurate representation of this function, just drew a random one, and I want to sum all those points up, right? Really what I'm doing is I'm finding the area under the curve. So the integral is going to do that, and then an average we divide by however many there are. Well, in this case we have 12. The book gives a formula. Instead of, divide n, we write multiplied by 1/12. So we're going to say this average is 1/12, right? That's dividing by 12. Integrate, we're going the first 12 hours. If it wanted 6 to 12, right, we could just do 6 to 12. But the first 12, we have 0 to 12 of that function. 47 plus 4t minus 1/3 t squared dt. Now we integrate, substitute the 12 in the 0, divide by 12. That would be our average. And always make sure it makes sense when you can. If I get something like 1,000 degrees here, I know that wouldn't make sense. All right, so integrate 47t plus 4t squared divided by 2, so 2t squared, minus 1/3 t cubed divided by 3, so 1/3 t cubed over 3, ranging that from 0 to 12, and whatever result we get, we want to multiply by 1/12. Okay, substitute 12 in here, 47 multiplied by 12, plus 2, 12 squared, minus 1/3, 12 to the third, so we could just say 1/9, I guess, right? 1/3, 3 times 3, 9. So, and then 12 cubed. Again, the 0 we don't need to do. If I subtracted and I plugged in 0 for all of these, right, they'd all be 0. And using a calculator off to the side, I saw this calculation would be nasty, so I went ahead and did it. Looks about 55 degrees is the average temp over this 12-hour period. Okay, one's not bad. This next one, you're going to need a formula. I want to take a quick second to explain what's going on though. What is this formula exactly doing? Okay, so we have some function. We're revolving it about a certain axis. Typically the x, but it could be the y. And that would change slightly. So without knowing what this graph looks like, this problem could still be done. But this is going to be a semicircle, right, from -2 to 2. And in fact, we could test that even really quick, right? Let's plug in -2 right here. That would be 4. 4 minus 4 is 0. Plug in +2. 4 minus 4 is 0. Plug in 0. 4 minus 0 is 4. Square root of 4 is 2. Plug in 1, we'd get square root of 3, and I don't know where exactly that's at, but I know it's less than 2, and anyways, trace the points here, you'd get this. Or use your graphing calculator or GeoGebra, or again, it really can be done without it. Okay, so we have this curve. We're revolving this curve about the x-axis, so picture this half circle doing a full 360 degrees around this x-axis. So as it spins around, right? Picture each of these points, I guess. I'm going to take this point and I'm going to spin it around the x-axis. Take this point, I'm going to spin it around the x-axis, and so forth. What would end up happening is we get a sphere here. Okay, it's taken that, and there are plenty of videos out there with much better drawings than me. Just wanted to show what's happening. And in order to calculate the volume of a sphere, or really all we need is r. But with an integral, what we are doing is we're actually calculating the area of these, well, volume, I should say, of these infinitely small disks here, which is basically the area of a circle. But picture a disk is just a circle, but then it has some sort of thickness. Well, we're making that thickness infinitely small, so really what we're doing, just like when we did over here the area under the curve, we're doing that area under the curve, but we're creating circles out of them. Well, the area of a circle is pi r squared. So it makes sense when we go to use this formula that this radius is whatever this function is, right? That's the height of that function. We square it, multiply it by pi, but we have infinitely many of those from -2 to 2, so we integrate. So the volume here, we're going to integrate -2 to 2, pi, and then instead of r squared, right, pi r squared, r I know is the function. It's square root 4 minus x squared. Squared, right? Pi r squared. So here's pi r squared dx. Pi is a constant. We could just pull that out. And -2 to 2, when I square this, it's a great example because it comes out nice and easy. Square root squared just cancels, so we're integrating 4 minus x squared dx. Well, this integral is 4x minus x to the third over 3 from -2 to 2. And whatever result we get, we multiply by pi. All right, let's substitute 2. We'd have 4 times 2 is 8 minus 8/3. Okay, that's substituting 2. Substitute -2 would have a -8, and then we'd have a positive 8/3. We've seen this happen a lot, actually, where we get the same thing, right? This becomes 8 and then plus 8, so 16. -8/3 and another -8/3, so -16/3. LCD is 3, so multiply that by 3 over 3. 48 minus 16 is 32 pi, right, times pi over 3. And we're doing volume, so whatever our units are, it's a cubic, right? Cubic units.